Hi everyone, and welcome to part 7 of this formal logic video series. In this session I'm going to look at some translations into quantified predicate logic. So that's going to involve going over how we can separate sentences in English into subjects and predicates, then looking how we can make translations of generalized statements using quantifiers and variables, and then finally I'm going to look at identity restriction and domain restriction. So first off, let's take a look at a pretty simple English sentence: John is happy. Now when we were working with PL, we would have translated that just into a single sentence letter, J, for John is happy. When we come to do PL, or QL as we sometimes call it, predicate logic or quantified predicate logic, what we're going to do is, instead of just translating entire sentences into a letter, we're going to split them up even further. So we can split this up into a subject, John, and a predicate. So the predicate here is happy. So it tends to be that English sentences have this kind of format. We have a subject with a predicate being applied to it. And what we're going to do is, so in PL, our atomic formulas were things like this, just a single sentence letter. What we're going to create is a new kind of atomic formula in QL. Let's just mark that's for PL. There's going to be a new kind of atomic formula in QL, which is going to involve identifying a subject and a predicate in each case, a coupling of a subject and predicate. So in QL, our subject, so John for instance, we might translate as a lowercase j, and all of our subjects will be lowercase letters from the beginning of the Roman alphabet. So we could have A, B, C, and so on, and we could also do this thing where we subscript, so we could have A1, A2, A3, and so on. So we've got an unlimited amount of subject letters that we can use, and these lowercase letters will stand for the subjects of English sentences. So this is where we've got a definite subject. We're talking about John in particular. There is someone who is John, and that's who we're identifying with this subject letter. Our predicate, so in this case we've got is happy, so we'll use a uppercase H for that. Predicates are all uppercase letters from the Roman alphabet, so A, B, C, and again we could have a predicate that was A1 or A2 or A3. So that gives us our translation of these two things, and now we just need to put them together. And what we'll do is, the convention within QL is that we always put the predicate first. So here we'd have H, J would be our translation of John is happy. So let's just do it. The quick translation here would be is happy. And I'll say a little bit more about writing keys in just a moment, but you can see here that this predicate H has one space for a subject to fill. So H and then whatever comes next means that thing is happy. So here we've filled that space with a J, so we get John is happy. And again, just to reiterate that this is now, this combination of a predicate and a subject is an atomic formula in QL. There's going to be a couple of other atomic formulas that we'll look at, but this is one kind of atomic formula. So in PL we just had this one sort where we had a subject letter in isolation, and this was the smallest building block of the language of PL. In our case, one of the smallest building blocks in QL is this combination of a predicate and a subject. So let's just say a little bit more about translation. Subjects are easy enough to translate, right? If we just have an A and we say Adam, that just means that wherever we see this lowercase a, that refers to Adam. And if we have an E, we can have Eve. Again, easy enough to make these kind of keys for subjects. For predicates, because we can have predicates with, at the minute we were just looking at a predicate with just one space. So we had H, and we said is happy. Now I would like to generally, I would probably write a little subscript 1 and 2 by these ellipses. So we've got ... 1, sorry, that shouldn't be 2, that should be 1 again. So we've got ... 1 means ... 1 is happy, right? So we can see that this space corresponds to this one in the translation. But we can have more than one placed predicates. We could have, I don't know, talked to. So let's say we've got the predicate T. That's got 2 spaces. So in our key, we'll write these 2 spaces, ... 1 and ... 2. Now, writing out that there's numbers there, putting these subscript numbers, is beneficial because it shows us how many spaces this predicate has. So now we can write our key here, and we can say ... 1 talked to ... 2. And what we've shown here is that the first space in the predicate, the first space for a subject letter in the predicate, corresponds to this space in the translation, and the second one translates to this second space here. But in writing T ... 1 ... 2, we're also showing that this predicate has 2 spaces and therefore needs 2 subjects in order to be complete. So if we just apply that quickly, if we had, I don't know, T A E, that's going to translate into Adam talked to Eve. And that's fine, and this would be an atomic formula that we've just created here, because we've got a predicate with all of its spaces for subjects filled in by subjects, right? All of the spaces that this predicate has is filled in, so it's therefore atomic, it's complete. If we'd had something like TA, and this is our translation, this just doesn't make sense. For a start, we're not sure where the A is going to go. So is this Adam talked to, or is it talked to Adam? Right, we haven't got 2 things here to show where how they coordinate with the translation. But aside from that, those aren't sentences with truth values. Adam talked to doesn't make sense in isolation. We need a someone that was talked to. And similarly, talked to Adam doesn't make sense unless we've got a someone, we know who it was that talked to Adam. So whenever, I mean, the point of writing a key in this way with a ... 1 and ... 2 is to show how many subjects need to be added in order that it can be complete and be an atomic formula. Right, TA on its own just doesn't make any sense. Also, if we wrote T, A, B, C, let's say if we had B and C had been defined as 2 other subjects, this again just wouldn't make sense. What's the C standing for? We've only got 2 spaces in this predicate. So where we've only got 2 spaces defining the key of a predicate, we're always going to need 2 subjects and only 2 subjects in order for that to appear in a sequence or a formula. So let's just quickly, we'll have another look at, suppose that we had, we can have more than 2 places. Again, we can have any number of places to a predicate. Some mathematical predicates might require dozens we're probably only ever going to need to use 3. So an example like this, for the predicate between, we might say that 1 is between 2 and 3. And again, what we've shown by writing out these 3 spaces is that in order for this to appear in a sentence, it needs 3 subjects. It needs 3 things to fill these these spaces that we've got here. And it also, of course, it coordinates it. It shows that this one goes here, this one goes to there, and this last one goes all the way to the end. Right, so it's coordinating, but it's also, I think the more important thing is that it's showing in your key that you've understood how many places these predicates have, and it allows us to make sense of when they appear in a formula. So if we have something like B, I don't know, A, E, J, remembering that we had J as John before, so that's going to be Adam is between Eve and John. And again, because we've got all three of the spaces filled in, this is going to be, again, an atomic formula, so it's complete. It can be a part of a larger formula now, whereas if we just had B, A, E, because we've only got two spaces filled there, it just doesn't make sense. How are we supposed to translate that? It's just not clear. And likewise if we'd had more than 3 subjects written after that. So now that we've identified our atomic formulas, or at least one kind of atomic formula, we can go on to just start constructing some basic formulas in QL. So all of the connectives that we had from PL we can still use in QL. So we had negation, and, or, if then, and if and only if. All of these, and of course we also had parentheses, we still need to use parentheses in order to avoid ambiguity. We can now apply these to the atomic formulas that we have here. So if we'd have had, suppose we wanted to say John is happy and Adam talked to Eve, now we can say that should be H, J, and we'll use our and symbol, and Adam talked to Eve. Okay, and we'd, to make it well formed, we'd bracket that. So there's one instance. Of course we could always add any other connective in here, right? If and only if, we could have a negation on the front. Right, the symbols work in exactly the same way as they would have done in PL. It's just now that our atomic formulas have changed slightly to be combinations of subjects and predicates. Okay, so just to recap, subjects are lowercase letters from the beginning of the Roman alphabet. Predicates are uppercase letters from the beginning of the Roman alphabet, or I think from anywhere in the Roman alphabet with predicates. Whenever we write a atomic formula in QL, sorry, the predicate always comes first. That's just our convention so that we can see. We might think that with something like Adam talked to Eve, maybe we might think it would read better that way, right? Adam talked to Eve with the T in the middle. But it's just messy. We want a simple language that's just got a set of conventions that we can follow easily. So in this case, the predicate always comes first, and we know how to translate them based upon the translation that we give. And looking again at translations, I would really strongly suggest that you write them in this way, that you have you show how many spaces there are for subjects in the translation of your predicate. So, H ... 1 tells me that it's a one-place predicate immediately. As soon as I look at your key, when I'm, if I'm marking your answer, if I'm trying to translate what you've got, I know immediately that that is a one-place predicate. T ... 1 ... 2. Even before I think about what it actually means, I know it's a two-place predicate. Right, and then I can see how it coordinates into that. So I'd really strongly suggest that you write your keys in that way. Okay, so there's a quick tour of subjects and predicates in QL, sorry. Now let's have a think about some more interesting stuff that we can do in QL. So sometimes we have sentences which aren't about any particular thing. So before we had John is happy, but suppose we had something is happy. I'll say something is happy and tall. Okay, so here we've not got something doesn't that doesn't refer to any one particular thing, right? This sentence, something is happy and tall, that could be true right now because there is maybe because John is happy and tall, but 100 years ago it could have been true because somebody else, Smith, was happy and tall. As this sentence can be made true by different subjects, right? Because it's general, it doesn't relate to any particular subject. Notice that this sentence, John is happy, presuming that John does refer to just one individual, that can only be made true by John being happy, whereas something is happy and tall could be made true by a number of different things. So we're not going to want a general subject, just a normal subject letter to represent something. We're going to need something slightly different, and for that, to translate this, we're going to need quantifiers and variables. So our quantifiers, I'll just write them in here. So we've got this backwards E, which is our existential quantifier, and then we have this upside down A, which is the universal quantifier. So these two symbols, they work in very much the same way as the predicates do that we've just looked at, except they only have one space and they must be filled by a variable rather than a subject letter, right? It wouldn't make any sense to write every John, right? Because John is a subject, so it doesn't make sense to say every John where we're talking about an individual. If we were making a general claim about people called John, that would be alright, but we do that in a slightly different way. Right, remember, the subject, this J, stands for the individual John, so to say every John doesn't really make a great deal of sense. What needs to fill the spaces of quantifiers are variables. So our variables will be something lowercase letters from the end of the Roman alphabet, so X, Y, Z, and again, as with the subjects, we could have X1, X2, X3, and so on. Now, a variable in QL works in much the same way that variables work in mathematics. So, if we saw an equation in maths, we saw, 4x equals 16. In this case, we can see that x equals 4, right? We just divide the whole equation by 4, so x stood for a particular number here, but it didn't have to stand for 4, right? In a different, if we'd had 4x equals 32, in this case, x stands for 8. Right, so in different situations, the x just stands for some number, right? It doesn't stand for any particular number. It can be a placeholder for any number of different numbers that we might have in a formula. So the same thing is going to happen with the variables that we use in QL. They could stand for any subject, but they don't have to be any particular one. They can just be any number at different times in different formulas. So in order to make use of quantifiers, what we need to do is combine them with a variable and bind a variable to that quantifier. So a variable on its own doesn't really tell us much. We need to show how what kind of quantification is involved. So the main combinations that we're going to get and that will be useful to us are EX, which means some X, or there exists an X. Right, so this is an existential claim. We're saying there exists something. There is something, and it has the following properties. That's how that's going to work. And of course, we could also have, just throw in our negation symbol here, not EX, which is going to mean nothing, or there is no X, such that. Okay, so this is going to be important in a minute when we're thinking about translating. Just remember that the negation of there exists an X means it's not the case that there exists an X, such that whatever these properties. So this is a way of saying that nothing has a particular set of properties. There doesn't exist anything with those properties, means that nothing has that set of properties. Okay, and then our AX is going to mean, I'm going to use that for all or every, say every X is such that. This is our way of introducing a general statement about a whole group of things, right? Everything is such that it has these properties. And then finally we can have the same where we've got a negation applied. This is probably the least used configuration of the quantifiers, not AX. That's going to mean not all, not everything. Not everything is, and whatever it is we're attributing to those to the variable here. Note that these two don't mean the same thing. These are non-identical, right? So this means nothing, whereas this just means not everything, right? So if I said nothing is female, that's clearly false. But if I said not all persons are female, then okay, that's clearly true, right? So they don't mean the same thing, perhaps quite intuitively. Okay, so we started off with this, and something is tall and happy. So now let's have a look at translating it. Now, just like when we did translations into predicate logic, we had to go through and kind of pick out, okay, so we've got, look, an and here, so that clues us into the fact we're going to have a conjunction symbol somewhere. Right, and we went through and we analysed the sentence and we looked for kind of buzzwords that would tell us what connectives we were going to be using. Now we can do the same thing but with our quantifier. So here we've got something at the very beginning. Now this relates to the existential quantifier, right? Some x, or something is such that, right? So whenever we see something, we know that we're, well, there's numerous ways we could say it, but the easiest way of saying it is going to be with existential quantifier. So something is tall and happy. I'm going to start off with there exists an x such that, right, and then I've got a bracket here that comes after it. Let's put that in brackets actually. So all these quantifiers go in brackets. Notice that the negation goes outside of the bracket, right? So the quantifier itself is what's the quantified statement, so the EX, the quantifier and the variable go within the brackets, and then the negation goes on the outside of that. Okay, so we've got there exists an X such that. So what was it that was true of this particular thing? Well, it's happy and it's tall. So let's suppose that we've got, sorry, one is happy, and we've got a predicate T, which means is tall. Then we can write HX and TX. Let's just move in this bracket a bit. So there we go, something is happy and tall. So we start off by showing what kind of quantification we're doing here. We're talking about an indefinite article, right? We don't know who it is, it's just something. So this can be made true by lots of different things. So we're going to be using a variable x, and it's going to be a existential quantifier, right? It's something. We're saying there is something which is happy and tall. There is at least one thing which is happy and tall. I guess we can see this as. So there exists this x, and what is true of that x? Well, x is happy and x is tall. So we just apply the predicates in much the same way that we did with where we did have definite articles. So before we had HJ, meaning John is happy. Now we just, instead of writing in a subject, the space that a predicate has, so our space here can be filled by either a subject or a variable. Sorry. And again, it needs this, but once we've filled that space with a variable, it's an atomic formula. So we can write it in much the same way as we did all our other formulas. Okay, one thing to kind of finally say is that we need to think about the scope of the quantifiers. So the scope of this quantifier is going to be the next bracket, right? So this quantifier, there exists an x, that binds x for this following bracket. And we need to bear that in mind because we can't have just like we can't have subjects on their own and we can't have predicates on their own without their spaces filled, it doesn't make sense to have, I don't know, just x on its own, or if we just had this formula. This doesn't make any sense because x is a variable, but we don't know how it's being applied here. Right? This could mean any number of different things. This could mean everything is happy and tall, or it could mean there's something that's happy and tall. It could mean there's nothing that's happy and tall. Right? How we quantify over the x, how we bind this x, is going to determine what the sentence comes out as. Now, supposing that we just had this, the scope of the quantifier is just the next well-formed formula. So in this case, the scope of this is just this sentence, right? It's just this one atomic formula, hx, because this is the next well-formed formula. It works in the same way as negation, right? If we have not A and B, going back to propositional logic just for a second, there's no ambiguity here, right? The negation has to apply to the next well-formed formula, so that's just going to be the A. If we want it to apply to A and B, we need to put brackets around A and B. And much the same is going on here. At the minute, the existential quantifier is binding x, but just for this formula. If we want it to bind it for both, we're going to need to put our brackets round. And we are going to need to do that because we can't have an unbound variable, which is what we would have had there. Okay, so another thing to think about, we'll move on to something else in just a second, but another thing to think about is when we need to use more than one variable. So suppose we have something is tall and something is happy. So in this case, I mean, suppose we were going through and we were analysing what we need to do to translate this. We're going to say, well, look, we've got this tall, so that's going to be a predicate. Let's say that's going to be, we're going to use a T for that. We've got happy, or is happy, so that's going to be an H. We're going to need these two predicates. We've also got this and, so again we're going to need our conjunction symbol. Now if we look through, we've got something here and we've also got another something here. Now in this case it looks like we might be talking about two different things. In the first sentence we looked at, something is tall and happy, it's the same something that is tall and happy. But in this case, while it might be the same something, could be that something is tall and that same something is happy, it's also open to it being that one thing is tall and then another thing is happy. So I think that means we're going to need two variables. So we'll use an x and we'll use a y. And how are we going to write that? Again, something that clues us in that it's going to be an ex, and again something ey. So we just have, there exists an x such that x is happy, and there exists a y such that y is tall. Okay, so now I did say that these could be the same somethings, but that's okay because remember that x and y could stand for any subject whatsoever. So suppose that suppose this sentence is true, something is tall and something is happy, and suppose that was made true. There was only one living thing in the universe, only one something, and that was John, and John is tall and happy. Suppose that that's the case. Well, look, our x could stand for John and our y could stand for John at the same time, right? They don't have to stand for distinct things. We're going to need some extra mechanisms in order to show that the x and y definitely don't stand for the same subject. So ex, hx and ey, ty means something is tall and something is happy, where they could be distinct objects or they could refer to the same thing. If we just used one variable, as we did up here, ex, hx and tx, then they have to be the same thing, right? X can only refer to, at any one given time, it's going to refer to the same thing when we're actually reading through the sentence. Although it could stand for lots of different subjects, if we say there exists an X such that it's happy and it's tall, we've got to be attributing those properties to the exact same thing in that one breath. Whereas when we use two different variables, we're talking about different things. So now we're in a position to do something useful with QL. So let's return to a syllogism that we will have seen many, many times. Say all philosophers are wise. So that's our first premise. We've got a second premise. Socrates is a philosopher. Therefore, conclusion, Socrates is wise. Okay, so there's a basic syllogism that maybe we've seen in some kind of configuration like that. Now, if we translated that into PL, we will probably already have noticed that, suppose we say that all philosophers are wise. Well, let's give that, let's represent that as A. Socrates is a philosopher. We'll let B represent that sentence. Therefore, Socrates is wise. C. This syllogism is valid from the looks of it, right? All philosophers are wise. Socrates is a philosopher. Therefore, Socrates is wise. If the first two premises are true, the conclusion must follow from them, right? It must also be true. But that isn't preserved in our PL translation, right? A, B, and C don't appear to have anything to do with one another. There's nothing that shows us that A and B are related to C in such a way that if A and B are both true, then C must be true. We need to go back to the English translation in order to do that. Well, now we're in a position that with predicate logic and with our quantifiers and variables that we can show why this is a valid sentence, or a valid argument, sorry, in QL. So let's go into our QL. Let's translate these two first. So Socrates is a philosopher. So let's say that, let's just do this at the bottom, that P is a philosopher, and W is wise, and we've also got a subject there, small case s, for Socrates. So we can just translate, let's translate premise 2 first. That doesn't require any quantifiers. Socrates is a philosopher. We know that our predicates come first and then our subject, so PS, and Socrates is wise. Well, again, we're going to have a large W and an S filling its space, right? We're saying that Socrates is the thing that is wise. Now we just need to translate all philosophers are wise. Translations of sentences like this, all philosophers are wise, or I know, all ravens are black, all humans are mortal, they all have the same kind of structure. Now let's look at it in isolation just quickly. Let's just say all F's are G's, right? Notice that has that structure. All philosophers are wise. If philosophers have the property F, then they also have the property G, being wise, right? So all F's are G's. Okay, let's break it down again. So we've got these predicates F and G. We don't need to write them out as letters again. We'll just understand that F is going to be property F and G is going to be has property G. We've got all, so that designates to us, if we go back over to our list of quantifiers, whenever we see all or every, everything, everyone, the easiest way of writing that is likely to be with a universal quantifier. So we're going to have AX. Now we just need to decide what it is that is going to go in between this. So it's going to be something like this. Every x is such that fx and then some connective gx. So we just need to know what it is that coordinates this. We've only got 4 choices, right? It could be a conjunction, a disjunction, an if-then, or a biconditional. Does a conjunction work? This would say everything is both an f and a g. Right? So if we applied that in our case above, if we translated this in the same way, that we'd be saying everything is a philosopher and is wise. So that's not right. If we used a disjunction, everything is either or everything is a philosopher or it's wise. In this case, everything's F or G. Again, that's not going to work. How about the conditional? Every X is such that if it has property F, then it has property G. Okay, so what we're saying there is we wanted to say all F's are G's, and this goes about it by saying that take anything in the universe. If it has the first property, then it has the second property. So that means that everything that has the first property has the second, right? So all F's will be G's if this is true. So whenever we have a sentence like this, all F's are G's, we'll always translate it as in this kind of way, right? Every X is such that if it has this property, then it has the second. So let's go back up to all philosophers are wise, and we can translate that as every X is such that if P X, let's use yellow for our variables as well so we can keep track of them. Every X is such that if it has property P, then it also has property W. So now, hopefully, looking at this, we can see why these two premises entail the conclusion, right? Because we've said that everything is such that if it has property P, then it has property W. S has property P. So just given this universal statement, we know that it must also have, if this is true, then S must have property W as well. So we've preserved the what it is that shows why this sentence is valid in using QL. So that's going to be really useful for us. Okay, so now let's just have a look at doing a few translations. So we've already looked at someone is tall and happy, and something is tall and something is happy. Let's look at a few more. So suppose we wanted to translate nothing is real, being anti-realist for the day. Let's just go about it in exactly the same way that we have been before. Nothing is real, so we've got a predicate here, is real. Sorry, we use an R to represent that. And then we've got a quantified statement, nothing, right? So again, if we think about this, we go back to, got like a little key here that shows us what we need. So nothing corresponds to not EX. So this is going to be not EX. Here is going to feature in this. So the variable that we're going to use is X. So nothing is real is going to come out as not EX RX. Okay. Notice that I don't need to put brackets around this part of the sentence, right? I don't need to do this. Not EX RX, because RX is atomic. So adding the brackets is, unless there's no rule that shows us that we need to add brackets, or that tells us how we can add brackets around just an atomic formula. Remember that from PL. So we don't need the brackets around that there. It can just be, oops, can just stand as it is on its own. Again, suppose then we wanted to translate nothing is not real. So we've got a double negative there. We wouldn't need to introduce a new predicate, right? We wouldn't need to redefine R, or to, suppose we just introduce another one, A, which is such and such is not real. Just like in PL, we can just notice that we can make use of the same predicate R, which was something is real, and we can just make use of a negation. When we've got a not here, this just designates to us that we're going to use a tilde, a negation symbol. So we'd have much the same thing. Nothing is not EX is not real. So what property is it that X has? Well, it doesn't have the property of being real. So there's nothing which has the property of not being real, and therefore nothing is not real. Okay. So let's move on to some more complicated examples. So this is quite a common one, or a common configuration. Every student sat an exam. Okay, so there's I've changed what will go on here, but there'll be a lot of examples like this. Anyway, every student sat an exam, every teacher shouted at a pupil, every mountaineer climbed a mountain. They all have a very similar configuration. So let's think about how we're going to start translating this. Okay, well, we've got, we're talking about students, right? So being a student is a predicate that we're going to need here, so we'll use S to denote that. We've got an exam, right? So is this, maybe we're going to, we'll use a variable to talk about this. So we'll say there's something which is an exam, right? And we'll use the property E for being, because we've got an exam, it's not the exam, it's not a definite article, it's just something. This could be true if, this could be true today because every student sat a particular exam or a set of exams, and it could have been true 100 years ago because every student sat an exam, that's different. So it's indefinite, and we'll use a variable to talk about it, and a predicate. So we've got E for is an exam and S for is a student. That means we've also got this coordinating predicate, right? Sat an exam, right? So there's another predicate here that looks like it's two-placed. In fact, I'm just going to change this slightly so that we can make use of more intuitive predicates. So if I'm going to say every pupil sat an exam, then we can have P for pupil and S for sat, where this is going to be two-place. Right, so this is going to be 1, 2, 1 sat 2, or 1 took 2. Right, so it's a two-place predicate. Okay, and now what else can we pick up from this? Well, look, we've got every, so that designates to us all, that designates to us our universal quantifier, so AX. We've also got an. Okay, so here's some, we can add to our kind of little cheat sheet here, right? Whenever we see some X or there exists an X, what we've really got here is an X is kind of like dropping the there exists. So if we see a something or an, again we're going to be using the existential quantifier. So the fact that we see this sat an exam, you can think, right, we're going to need an existential quantifier here, and it's a different thing, right? It's not, the pupils in the exam are different, so it'll be a different variable. Yeah. Okay, so now let's think about how we can go about writing this. So we want to say every pupil sat an exam. And I think it's going to be instructive to think back to the all philosophers are wise example that we looked at before here. We're going to start off with our every X is such that, and we're going to have a wide bracket here. We want the scope to go all the way across this. So every X is such that what? Well, we want to say that, basically we want to say all pupils sat an exam. So let's remember our sentence we had up here, and we had all philosophers are wise, and that turned into AX, PX, then FX, or in fact let's look back down at our all F's are G's. In this case we're saying that everything that is a pupil had the property of sitting an exam. Right now the sitting an exam bit is kind of a bit more complex, but really what we're saying is that every pupil had property X, right? And property X is the property of sitting an exam, right? So where this is, that's going to turn out to require some slightly more complicated. It's not just one particular thing. In this case we've just got GX, right? The GX here is going to be a lot more complicated in our translation, but it's nonetheless the case that we're making a similar kind of statement, right? Everything that was a pupil, or everything that is a pupil, has the property of sitting an exam. So we can start off in the same way, right? It's going to have the same kind of structure as this. So every X is such that if X is a pupil, then something is true of it. And the thing that's true of it is that it sat an exam. So how are we going to go about saying that? Well, because we need to make this existential statement, another way of saying this second property is that every x is such that if it's a pupil, then there is something, that thing is an exam, and the pupil sat it. Right, so we're going to need to say there exists a y such that, and we'll give it again a bracket, y is an exam and x sat y. Okay? So just let's go over that again slowly. We wanted to say every pupil sat an exam, and we've noticed initially that that has a very similar structure to our all F's are G's, right? All pupils had a particular property, this next property, sitting an exam, right? So we began in the same way. This is just kind of like the first half of our all F's are G's bit. But then the second property, the conditional of that, the consequent of that conditional, was slightly more complex. So we wanted to say that every x is such that if it's a pupil, then there is some y, there exists a y, such that that thing's an exam, and they sat it. Okay. Now this structure is going to be crop up a lot whenever we want to make a statement like this. Every teacher shouted at a pupil. Every mountaineer climbed a mountain. Right. It's always going to have a very similar structure to this, or at least we're going to be able to write it in that way. But things are slightly more complicated than that. Every pupil sat an exam is actually ambiguous. It involves a scope ambiguity, and we can use QL to show that scope ambiguity. So this sentence isn't ambiguous. Right? We've removed all the ambiguity by putting it into quantifier logic. The ambiguity arises in the order in which the quantifiers appear, so which quantifier takes wider scope. So in our case, the universal quantifier takes wide scope. Right? So this is a sentence about all pupils. If every pupil is such that there exists some exam and they sat it. Right, but there's another meaning to this, which is that there's just one exam and every pupil sat that particular exam. And in that case, it's going to be that the existential quantifier takes wider scope. So let's think about how we'd say that. We want to say there exists an exam. So let's have there exists an x such that x is an exam, and then we want to say that every pupil sat it. So we'll just say and for all y, again, every pupil sat this thing. That's the same kind of every f is g, right? So every y is such that if it has the property of being a pupil, then it has the property of sitting. It's got to be the other way around, hasn't it? Y sits x. So there we've got the quantifiers the other way round. Our existential quantifier takes wide scope over the universal quantifier. And so these two different configurations show the scope ambiguity. In this case we're saying, I guess a way to think about it is in the first case it's like we're saying take all the x's, right? So here's the column for the x's. Right, so here's an x, here's another x, here's another x, here's another x, and so on. We could go on forever like this. And however many x's there are. So for each x, there exists a y, right? So this is the column for the y's. So for each one, there exists a y. Now we kind of apply this second bit. The existential claim is applied to every single x. Right, so every x is such that if it is p, okay, so maybe we should have made clear that these are the x's which have property p, right? So every single one of these, for every x, if it meets the condition p, if it has that predicate, then there exists a y. So there's going to be lots and lots of y's. In the second case, we're saying start off with our got x, we're saying there exists an x, or there exists at least one, but it's open to there just being one x, right? But it's the case for this one x that every y, if it has property p, so this is all the y's with property p, kind of linked out. So this is a many-to-many relation, whereas this is a one-to-many. Yeah? I guess that's the way that I would visualize this scope ambiguity. In the first case, every x is such that if it has property p, so here's all the x's that have property p, then there's an existential claim for each one of those, right? So there's however many existential statements as there are x's that have property p, whereas in this case, it's just one existential claim that we're making, right? There is at least one exam such that everything which had property p took it, right? So there's the difference between having one existential claim and having one existential claim for every single one of the things that we're quantifying over. So there's a difference between the two different readings of that sentence. Every pupil sat an exam. And again, you might be given a sentence like that, every pupil sat an exam, and asked to demonstrate why it's ambiguous, or say why it's ambiguous, and kind of resolve the ambiguity. Write it in QL in such a way that it is no longer ambiguous, or write both ways to show that you've understood this kind of scope ambiguity that's going on here. So it's worth remembering this formulation because it is going to come up most likely again and again and again. Okay, so there's a few examples of translations into QL. Now let's move on to think about restrictions of identity. Oops, picked a grey. So, identity restriction. Now in QL, identity, we're going to need some new symbols, but identity restriction is really very easy. It's as simple as just writing x equals y. So this is how we state that x is equal to y, x is identical to y. And any subject or variable could fill. So we've got a new constant here, this equals symbol, and it has two spaces, one on either side of it. Again, just like all of our predicates, it needs something to go in these spaces in order that it be, let's use meta variables in fact here. So we've got phi and psi, where this phi or psi could be any subject or variable, and it needs those there in order for it to make sense. And hopefully that's quite intuitive, right? If we just say a equals and we don't say what it equals, then that we haven't said it. We need to know what it is that a equals or a is identical to. Now once we've got it where it's filled in on both sides, this again is another kind of atomic formula. So we've got let's just make a note of that. So QL atomic formulas. So our atomic formulas in QL are going to be any time that we've got, say, a predicate with all of its spaces filled. So let's change that to AB. Anytime that we've got that, or if we've got, if it's two place, C, D, E, right? So long as all of the spaces of the predicate are filled with subjects, then, or with a variable, I guess, we could have A, X. So whenever we've got a predicate, sorry, in fact, that's going to be our, let's say that that's our second. So when we're using subjects and predicates, whenever we've got a predicate with all of its spaces filled by subjects, that's atomic. Same goes for if we use variables instead, so AX or C, XY, or if we've got B, X, Y, Z. Those are going to be atomic. And then we've got this third kind, which is where we've got X equals Y, or we could have subjects in there, A equals B. Right, so these are the atomic formulas that we can make use of. We could connect these with a symbol, a conjunction, and we wouldn't need to bracket them because they're atomic, right? A is identical to B is an atomic formula of QL. So just like if we had A and B, we don't need to bracket B or A because they're atomic. Exactly the same way, we don't need to bracket any of these if we combine them with a connective. Obviously, if we combine more than one, so if we have this, we need a set of brackets around one of the complex formulas, so those formulas that involve atomic formulas and a connective. We need to bracket those so that we can see which is the main operator of these sentences. Okay, so let's go back to identity. Again, very, very easy. We just need to say that x is equal to y. We just write that. If we want to say that two things are non-identical, then we just add our negation onto the front. Now notice, again, we don't need to write this. Tempting as it might be to bracket, let's make sure that doesn't look like the predicate x. We don't need to bracket around the identity statement because it's atomic, right? And a negation just applies to the next atomic formula. There's not really any sense in if we said not x is identical to y. What does not x mean, right? What is this? X is a variable. It refers to to some subject, some indefinite subject. So it can't be. You can't negate a variable or negate a subject. It's not the kind of. You can only negate things that have truth values, right? It's a not statement. It reverses the truth value. That was our. If we think back to our truth tables that exhaustively showed the meanings of the logical constants, the meaning of the negation symbol is just to reverse the truth value of a proposition. But x isn't a proposition, it's a stand-in for a subject, right? It's a variable. So we would never need to add brackets around this because this can only mean x is not identical to y. Okay? So let's now have a think about when this would be useful. So for a start, it's going to be useful in when we want to show that a particular variable is either identical to a subject that we've identified or that it's not identical to a subject. So if we take this, I don't know, let's think of a sentence, something ate the last cookie and it wasn't, terrible handwriting, it wasn't Julie. So here we're going to need some kind of identity statement here. We need to say that something ate the last cookie, but we also need to say that that something is not identical to Julie. Okay, so again, let's just go through. We've got ate, so we'll give that looks like a two-place predicate. A, one thing ate another. The last cookie, maybe we'll just call that a single predicate, right? Being the last cookie. That's just a one-place predicate, being the last cookie. We've got this quantifier, something, so we know that we're going to be using ex, and we've got Julie. So we'll use a lowercase j to represent Julie. Obviously, I'm just doing this quickly. In your exam, make sure you write out a key properly. So you kind of write out every single one of these. So j is Julie. You do each of these keys for the predicates properly. Oh, and sorry, we've got this connective. Right, so we know that we've got an and there. So in fact, it looks like as our language goes, actually, the last cookie is a definite description. So we'll return to this in a second, how we might say otherwise, but let's just give this a subject letter for now. The last cookie is just a small case c. Just to make things a bit simpler, we'll make it a bit more complex in just a second. So something is going to be there exists an x, and what's true of that x? Well, x ate the last cookie, so we're going to want to say 8xc, and we also want to say that it wasn't Julie that ate the last cookie. Right, so X is not Julie. So not X equals J. Okay, so there we go. It's as simple as that, using the identity statements. Just to say, you know, there is something which has this property, and it's not this other thing, right? Okay, when else might we use it? Well, we might say that, we might want to say that if two things have the same property, then they're the same. So maybe we want to say if Superman and Clark Kent, let's say if Superman and Clark Kent can both fly, then they are the same person. Okay, so this sentence probably, I don't know whether this turns out to be true. Maybe it's possible for Clark Kent to fly and Superman to fly in some possible world and then not be the same person. Maybe it doesn't express a necessary truth, but it can at least illustrate where we can use our identity statement. So we've got, we use a small case S for Superman, a small case C for Clark Kent. Fly, we'll use an uppercase F. And the same person, well, we'll just understand that that's an identity statement, right? They are the same, they are identical. And we've got an if-then as well, so if we pick out our predicates, we've got an if-then, and we've got a conjunction. So then let's set about that. So we want to say if S has property F, and C has property F, so that's the antecedent, that's the condition, then S equals C. Okay, so there we've just said if S has property F and C has property F, then S is identical to C. Again, I'm not sure whether that turns out to be true. Maybe we can think that there's a possible world in which Superman isn't Clark Kent, so therefore it's not necessitated in any way, or it's not really entailed that they're the same person. But nonetheless, we at least get the idea of how we can translate using this identity symbol. Perhaps it makes more sense if we'd have said something like this. If we'd have said, if Batman has blue eyes and Bruce Wayne has brown eyes, then they are not the same person. Okay, so here it makes a bit more sense, I guess we might say this. So we say that that's that little case, small case b is Batman, and small case w, lowercase w is Bruce Wayne. Then we want to say, and let's say that's blue eyes. Oh, I should have picked a different green. I should have said blue. Let's just call that property A. We can say if Batman has blue eyes and Bruce Wayne has brown eyes, there's the condition, then they can't be the same person, right? Because they've got conflicting. Or maybe we should just say, and Bruce Wayne doesn't have, maybe that would have been a better way to say it. Bruce Wayne, let's get rid of the has as well, doesn't have blue eyes. And then we can see it as well why that would be the case. So doesn't have blue eyes. So if these two things, if B and W have conflicting properties, right? B has property B and W doesn't have property B, then B, then it's not the case that B equals W. Okay. So there's another case where we might use that. Okay, the other thing that's going to be useful, that this is going to be useful for, and then we'll return to our cookie example, don't worry, more on the cookie. The other thing it's going to be useful for is when we want to say that there's just one thing that has a particular property. So here, when we use existential statements, we understand that to mean there is at least one x. It could be, if we say there's something which is tall and happy, if there are 3 things that are tall and happy, that's fine, it's consistent with that sentence. If we wanted to say there's exactly one thing which is tall and happy, or there's exactly one thing that has property p, we're going to need to use some identity statements to do that. So let's say, if we want to say there is exactly one f, how are we going to go about that? Well, we know we're kind of making an existential claim anyway, so there exists something, and that thing has property x. But what else needs to be true? Well, if there's only one f, it means that if anything at all has the property of being f, it must be identical with that thing, right? Because there's only one. Suppose if I said there's only one Batman, and we know that Bruce Wayne is Batman, let's say, and then I say, oh, but John Smith is Batman too. Well, John Smith must be an alias of Bruce Wayne, because if it's true that there's only one, then if anything else is also Batman, they must be Bruce Wayne, right? So we'll follow this up with this sentence, and for all y, if y has property f, then x equals y. And we'll close our outer bracket. So remember, we need to make sure that the existential quantifier has scope over all of this, so the bracket needs to go from the beginning to the end, because we've got an x here that needs to be bound to this variable. So that's how we're going to say there is exactly one thing with property f. Okay, there's just one thing. So now let's rethink our something ate the last cookie and it wasn't Julie, because initially I was going to use a quantifier for this, but then I changed my mind because we hadn't talked about identity and saying there's exactly one thing. Now let's have another look. So let's go down and say something ate the last cookie and it wasn't Julie. Okay, so this time, if we want to say the last cookie, let's say we're going to use a quantifier to describe this. There is something, and it's the last cookie, and there's just one thing, right? If any other thing is the last cookie, then it was identical with that first thing, right? There's only one last cookie. So we're going to need this identity statement. Now it's going to have very much the same structure, we'd hope, as this, but it's going to have the same overall structure, but there's going to be something added. So let's start off at the beginning. So something ate the last cookie. So there we've got, there exists an x such that x ate the last cookie. So there's something which is the last cookie we're going to need to say. So let's have another existential statement here. There exists an x such that there exists a y such that, and let's say, again, I think let's use an uppercase C for this. So we're going to want to say, let's give me some more room here because I'm not sure. In fact, let's use a different colour so we can designate. This is our outer bracket for the whole sentence. In fact, we don't need that there. Let's use a yellow so we can see what we're doing with the y. So this bracket, the ex has scope over this whole thing. Because it has scope over ey and ey has scope over this whole thing, it has scope over the entire thing. But I just want to show where we're adding in the bit about the last cookie. So there exists a y such that so y is the last cookie, and for any z, if z is the last cookie, then y equals z. So there's our bit about, so there's something which is the last cookie, and then what else do we want to say about it? Well, we want to say that x ate that thing, right? So we had and ate xy. Gonna need another set of brackets here, and x does not equal Julie. Okay, so I'm going to need to shrink this down, I think, so we can see it all. Let's just make that a bit smaller. Okay, so we've got there exists an x such there exists a y such that x is the y is the last cookie, and every z is such that if it's the last cookie, then y equals z. So there we've implanted there is one and only one thing which has this property, right? We want to say that there's just one thing which is the last cookie. So we've slotted in this kind of structure. Sorry, where are we? This structure that we had here. We've just implanted that into this here, and then we've kept the structure that we had before. We need another bracket here. Albeit that we've got the brackets in a slightly different configuration, but in fact, let's kind of change it so it is the same. Let's get rid of that bracket. So we'd need that. So notice that the blue bits are just what we had before. Right, so we had something ate the last cookie and it wasn't Julie, and we said there exists an x such that x ate the last cookie and x is not equal to j. So all that is now just the blue bits that we've got down here. Should be in brackets. Right, so that's just this bit. There exists an x such that x ate y and x does not equal j. Right, and what we've done is we've added in something extra to show that what y is. It is just one thing, and it's the last cookie. That's what we've done there. We've implanted that. So there we've got a way of saying there's exactly one. Something to go away and think about is how you could say there are exactly two f's. So we know how to say there's exactly one f. How would you say there's exactly two f's? How would you say more than two? F's. So this is going to involve saying that there are at least two things, but there could be more, right? Maybe go away and think about how you construct these with the quantifiers and with the identity statements that we've got. Okay, so the final thing that I just want to touch on is domain restriction. So at the minute, whenever we use a variable, it could refer to just anything at all. So if we wanted to say someone likes everybody, supposing that, if we see that someone is going to be an EX, the everybody, because we've got every, that designates that it's going to be a universal, and we've got an L for likes, it might be nice to think that we could just write this as there exists an X such that for all Y, should be in brackets, X likes Y. But our problem is that X and Y can refer to anything. So suppose that X referred to a table and X referred to a chair. Remember, X and Y can stand for anything at all. What we would have said with this statement is, well, possibly something like some table likes every chair, or likes a chair. Right, that's consistent with this. It seems to be entailed, or not entailed by it, but it's at least consistent with it. And we don't want it to be consistent with it. We're talking expressly about people. Now we could get around this by using a predicate for person. So someone, whenever we see someone, suppose we'd seen some elephant likes every elephant, we'd need a predicate for elephant, right? Some elephant. Well, here we've got someone, and one designates a person. Everybody, again, is going to be a person. So we could have gotten around it by saying every X is such that, there exists an X such that X is a person, and everything which, and they like everybody, right? So everybody is liked by them. Every F is a G means we're going to have every Y is such that if y is a person, then x likes y. Yeah, so we could have gotten around it like that, but that's kind of messy. It required a lot more architecture, and where we're going to get a lot of predicates thrown in, it's going to get more and more complicated to account for all of this. But we were always just talking about persons, right? There's nothing else being talked about here. So another way around it is to restrict the domain of our variables. So we'll just write something in our key that shows whenever we use a variable, it's just going to refer to something from the class of persons. Right? We restrict the set of things that we're talking about. And the way we do that is by adding in our key this little, so we have this curly bracket, and we'll say x is a person. So now with that, if that was in our key, so let's write a key for this one. So we've just got likes is our only predicate there. Sorry, it's two place, 1, 2. So 1 likes 2. With this in our key, we can just write there exists an x such that for all y, x likes y. And we know we're talking about persons because we've restricted the set of things that can be pointed to by the variables. Now it's really important that we understand what we're doing here. Right? We're not. This isn't like the other bits in our keys, right? We're not saying that x is a person. We're not saying that the variable x. When it's not like when we write s is Socrates, right? So we couldn't. Don't be tempted to write all of your key like this, where you're going to write s is Socrates. Right? It doesn't work in the same way. Subject letters we just define like that. S just equals Socrates or just refers to Socrates. Here what we're doing is showing that we're restricting the set of things we're talking about. So you wouldn't need to do this for y as well. Right? It's tempting to think that here I've said x always refers to a person, but I also need to say that my other variable y always refers to a person too. But we don't need that. Okay? So long as we've got this just means that every single variable, let's write that here. So every variable refers to a person. Right, so the y, if we had a z in there as well as another variable, again that would refer to a person. It restricts the domain for every single variable.